So here we defined, we mentioned briefly what SLE curves satisfy properties. And so we look again at the previous results. So the uniformizing map of an SLE is when you pick an SLE from minus I up to I in the unit disk, and you look at the domain which is to the left of the curve. And then you take the map from that domain to the unit disk, fixing the points I, and minus 1. This results in mapping it to the unit disk and mapping the SLE curve to the boundary of the disk. Then this map phi is called the uniformizing map. And a priori, it's not clear what should be the regularity of it, because you're mapping some fractal object to a smooth curve. But it was shown in a paper by Gwyn, Miller, and Sun in 2018 that this uniformizing map is actually Hölder continuous for the case kappa is not equal to 4. And of course, things look slightly different when you take a boundary intersecting curve that is kappa greater than 4. But you don't have to worry about that, because this image is mostly relevant because the way we define the uniformizing map is the exact same for the SLE4, because it's not boundary intersecting either. So that was the first result. And the second result is that for SLE, for kappa is not equal to 8, the curve is almost surely locally Hölder continuous, and the optimal Hölder exponent is determined. And this was determined by Bieklund and Lawler. So we will have parallels to these two results, and another one, which is relevant in the context as well. So the first one is the modulus of continuity of the uniformizing map for SLE4. So basically ignore all of what's written here. It's just a lot of text to get the theorem here, but it's just describing the setting, which was the picture on the last slide. So basically, for every zeta greater than 0, we get this bound here with a random constant, and this so we get this logarithmic bound on the modulus. This is the modulus continuity that we get. So the distance between phi of z and phi of w is bounded by the constant times log of 1 over z minus w to this exponent. However, this is very sensitive. This is basically optimal, because if you were to pick any negative zeta instead of positive, then this would almost surely not hold for any finite constant, because this quantity here is almost surely infinite. So this really gives us the threshold for when it works. Yeah, so this is more or less the optimal modulus of continuity that you can get here. Of course, we don't know exactly what happens at minus 1/3, where you don't add this zeta, or so that's the case we don't know yet. This is close to optimal, and it fills a gap in the literature. And to speak about the next result, I will introduce the notion of conformal removability. So say that a set K, a subset of the complex plane, is conformally removable if every function phi from the complex plane into itself, which is conformal outside of K, is also conformal on K. So basically, this kind of says that the set K is not too big, because it cannot mess up the map too much by not. Being conformal outside of it implies being conformal in it. And this is important when talking about conformal welding. You do this by, you take disk D1 and disk D2, they're copies of the unit disk, and you take a homeomorphism from the boundaries. Then a conformal welding with welding homeomorphism phi consists of a closed curve on the unit sphere. So here drawn in red, this is eta, It goes all the way around back. And this sphere here, and two conformal maps, psi j for j is equal to 1 and 2, which take dj to each of these components. So this is and then make sure that this composition of the inverse map and the forward map here is equal to the boundary homeomorphism. So this encodes a way to glue these two disks together to form a sphere. And a priori, it's not clear at all that that this curve here should be unique. Maybe you could glue them together in a lot of ways and produce different curves. However, if you know that if you can glue them together to form a curve eta, and you know that this curve eta is conformally removable, then you know that it is the only curve that can arise from the welding homeomorphism. So knowing that a set is conformally removable gives you uniqueness, and that turns out to be very important in many applications. So people have studied ways to prove that certain sets are conformally removable, and a paper which is usually cited and which is basically the collection of sufficient conditions, is a paper by Jones and Smirnov. And it follows from these conditions that SLE kappa is conformally removable for kappa is less than 4, which is great because then this gives us a way to know that when we glue together certain quantum surfaces, which is random surfaces with some conformal structure, which are incredibly powerful in our field, you know that when you glue them together, then you get something unique. However, it's an open question whether SLE4 is actually conformally removable. And our first result is somehow discussing this problem. So you can basically ignore this. If you don't know what quasi-hyperbolic distance is, then fine, read it, but it's not really important to understand. Jag håller föredrag. Okay, sorry about that interruption. I'm sitting in a hotel room and I was interrupted. Okay, so basically this just says here that the quasi-hyperbolic distance, when you integrate over the domain with respect to a fixed point here, will be infinite. And this contradicts all of the results in the Jones-Smirnov paper as soon as you choose the quasi-hyperbolic geodesics, which are the easiest geodesics to work with there. So this suggests that if you want to prove conformal removability of SLE4, then you should probably look for other ways to do it. I mean, we don't even know if it should be conformally removable yet. So it's really a big question. And the last of our theorems is on the modulus of continuity of SLE8. So it's basically for any fixed p, there's almost surely a constant c greater than 0, so that the distance between eta at two different time points is bounded by this log of 1 over s minus t to the power of some exponent which is slightly larger than minus 1/4. And this is also clearly this is not Hölder continuous, which is compared to other SLE cases. And moreover, this looks very much like the modulus of continuity for the uniformizing map of the SLE4. And that's because they basically arise from the same kind of estimate. This proved a conjecture by Alvisio and Lawler from several years ago, and so this constitutes the final good result on the modulus of continuity that is needed for SLE. However, we still don't know here. Does it work if we just pick zeta is equal to 0? Will it be will it be bounded or will it diverge? So that's we cannot decide that yet. So I'll just briefly explain how we actually approach this problem. So the main motivation is that the escape probability of a Brownian motion started very close to the curve can be compared to several important quantities. So first, if you take the derivative of the uniformizing map, this is for the first SLE4 result, and you pick, say, a point z here, very close to the curve eta, say within distance epsilon to the curve, and you want to know the regularity of the map. Then it's natural to start with the derivative of the map. And it can be, using the curve 1/4 theorem, you can, this is up to constants equal to the distance between the image point and the boundary divided by the distance between the first point here and the boundary here. So basically we want to, so if we just say that z here is within distance epsilon of the boundary, we want to know, okay, so how far from the boundary is this point here? And so suppose now that we have this point here and we start a Brownian motion. The probability that a Brownian motion does not hit the curve, but actually goes out and hits some region which is macroscopically far away, because we were considering epsilon going to 0. Then the probability of making it far away here to hit something at macroscopic distance is roughly equal to the probability of getting away from the boundary here and hitting this big yellow circle in the middle. And the probability of hitting this circle in the middle here immediately translates to the distance from this point to the boundary. This is just some elementary complex analysis estimates. So basically, by investigating the escape probability of Brownian motion here, we get the distance here, and together we get this gives us the derivative of the conformal map, which then gives us a way to extrapolate the modulus of continuity for the map here. And similarly, one can see that you can compare the escape probability of Brownian motion to the quasi-hyperbolic distance and to half-plane capacity of a set close to the tip of the curve. But I will just talk briefly about the SLE4 case. Yeah. So basically, we just need to know what's the probability here of escaping, given the curves. So just 20 seconds about Levy quantum gravity. So this is a family of quantum surfaces, which are models of random surfaces which have a measure and a conformal structure. They can be parameterized by any simply connected domain, and they can be cut by SLE-type curves to give new surfaces. You don't need to know more, because I have basically one slide of simple things to do to get the main estimate. So you start with something called a quantum cone, and you define you pick two SLE curves, let them run there, and let them be independent of the surface you define them on.
Sorry, Lukas. So if you could, maybe you can try to conclude in 1 minute or so. Would that be all right?
Yes, I am. I'm almost done.
Okay, great. Thanks.
So then this divides the quantum cone into two surfaces, two quantum wedges. And then you can, since it doesn't matter which simply connected domain you parameterize it by, you can just map it to this domain here, to the strip. And the escape probability of a Brownian motion, I mean, a Brownian motion is conformally invariant, so the probability of escaping far from 0 here is the same as the probability of going far to the right here, as long as we map 0 to -infinity in the strip. And we know how to control a Brownian motion in the strip. So that's something easy. So we just need to make sure that this is not too far to the right or too far to the left. So doing moment estimates, we know that this here, this ball, and therefore also the image of the ball, does not have too small or too large mass. We know also that this the quantum wedge here, parameterized by the strip, has very small mass far to the left and quite large mass far to the right. So this means that it cannot be too far to the left because it has too large mass to be far to the left. And this image cannot be too far to the right because it has too small mass to be far to the right. So we have basically a region where this image can be, which gives us a bound on where the probability of escaping for the Brownian motion. And then you just say that, oh well, I mean, locally around 0, this looks just like the SLE4 curve that we're interested in. And then you do some magic with conformal mappings, and you can get the theorem. So basically, we're just in the phases: strategy for proving estimate, something, profit. And this here, turns the paper from 20 to 25 pages to 90 pages, but it's doable. So yeah, sorry for taking extra time. I got a bit off track. But thanks for listening.
Thank you very much. Thank you. Perfect. So our next speaker is Janne Junnila, who's a neighbor from Lausanne, EPFL, who's going to talk about reconstructing the base field from imaginary multiplicative chaos.
All right. First of all, thanks to the organizers for the invitation. I'm very happy to talk here. What I will be talking today is kind of a cute little problem we were studying with Johannes some time ago. The problem itself is basically just the title of the talk. So I will start by trying to explain what these words in the title mean, and then hopefully we will converge to some kind of solution. So let me start with local-ordered Gaussian fields. So a local-ordered Gaussian field is just a field whose covariance is given by the logarithm plus something regular compared to the logarithm. So this is a heuristic definition, and then as we saw in the first part of the session, Antoine and also Hugo, they said that this is actually not the point when it's defined, but rather it has to be understood as a distribution. And this means that for two test functions, the covariance of the field applied to the test functions is given by this integral where you have this covariance kernel. So kind of the prototypical example is the 2D GFF, which also was discussed last hour. So it's simply the case where the coefficient, and here is a picture. You already saw several of similar pictures. So I think I won't actually talk more about this. It's related to various applications and so on. But the topic of this talk is more kind of a pure math little bit problem. So I will just move on. Gaussian multiplicative chaos, which was also introduced a couple of times, except now I'll allow this parameter gamma to actually be a complex number. So Gaussian multiplicative chaos is basically just the exponential of a localized field multiplied by some parameter. In order to rigorously define this thing, you have to approximate this field X with some regular fields and then renormalize. So there is this story, it involves many people. First it was studied in the case where gamma was real, and then there are also results for when you choose a suitable gamma, which is a complex number. And what you can show is that if you renormalize by adding this factor here, minus gamma squared over 2 times the variance, which by the way is chosen in such a way that the expectation of this whole thing is 1, then you converge to a random distribution. And this is quite robust in terms of the way you approximate this field. So you can choose many different kind of approximations and you will get the same result and so on. But that's not very relevant in this talk. So then we just call this limit the GMC distribution associated with the field X. So what are suitable gammas? The suitable gammas are gammas located in this so-called subcritical phase. It's this kind of I-shaped domain. There's in the middle there's this disk of radius squared of d, and then you attach these two line segments in 45-degree angles with tips at the square root of 2d. And everything inside this disk is a pseudo-gamma. And in fact, you can construct this distribution simultaneously for all gamma, and this mapping from gamma to the chaos distribution will be a vector value analytic function. But today we will be only interested in what happens here on the imaginary axis. So our gamma will be purely imaginary. And here's basically just a theorem from 2 slides ago restated in this thing where I have set gamma to equal I beta. And now you can notice that here actually we had minus before, but because there's an I, it turned into a plus. So what you have to do is you actually blow up this regularized version so that when this first term here with the I starts to oscillate a lot, then this plot will actually kind of exactly cancel this effect of the oscillation, so you get some limit. And you can take the limit in some, let's say, some Sobolev space of order which is negative enough. Let me also very briefly mention that there's also at least one natural model where this object appears, and this is the so-called Xoor-Ising model, which is obtained by taking two independent Ising models at critical temperature. And okay, so here in this picture, they are both chosen with a zero boundary condition. And then let's say that the spins take values plus and minus 1 in each cell in this grid. And then you just multiply together the spins of the two independent Ising models, and that's the Xoor-Ising model. And then if you, in this picture, let the lattice size go to 0, and you also have to introduce some kind of blow-up, and this spin field converges to the real part of this imaginary with a certain parameter to the minus half. Okay, so that's just one example, but I would be interested in kind of the more general case, and I'll talk more about that. So kind of another motivation to studying these chaos distributions is to ask what can you actually tell about the field by looking at them. And if you look at the real multiplicative chaos, during the first half of the session, it was mentioned that actually this real chaos it's supported on the so-called thick points of the field. And so the thick points are the points where the field scales roughly like when you take this approximation. So a priori, at least, it's actually dependent on the sequence of approximations. But I guess if you do kind of reasonable approximations, they should give you the same result. So it's the points where it scales like gamma times the variance, and somehow this leads to actually studying the high points of the field by using this chaos measure. So okay, and then you could ask, can you say something? Is there some natural property of the field that you can study using the imaginary chaos? And this is, at the moment, it's much more hazy, it's a somewhat open problem, but at least I can say that it's been used to compute the Hausdorff dimension of two-valued sets of the GF. So they are kind of a Leveland type of sets. So this was by Schoug, Sepulveda, and Wiklund recently as well. So there's a kind of good chance that the imaginary chaos is somehow related to more geometrical features of the field. All right, so the topic of this talk is actually kind of more fundamental and basic question, which is what information about the field is even in principle retained in this imaginary chaos. In particular, is this field a measurable function of the chaos? So here on the left-hand side, we have an instance of the Gaussian free field in the unit square. the blue points are the points where it's lower value, and the red points are where it's a high value. So of course, this is again just some approximation because you cannot really draw pictures of the field. And then you take the imaginary chaos, and you get this image on the right-hand side. And now you ask, can you actually somehow look at the right-hand side picture and go back to the left-hand side picture in some way? And so what we were trying to do is we are trying to recover the field from the imaginary chaos. And I was just saying that in the case of the real chaos, this is actually already well known for some years that you can do this. You have actually quite nice way of recovering it. You just take the logarithm of the mass of a small ball. You center it by subtracting the expectation, and then you take the limit. And in some suitable topology, this will converge to the original field. However, if you are trying to kind of just do the same thing for the imaginary chaos, then the positivity of this guy is lost, and you would have to start worrying about branches of the logarithm and things like that, and it basically just breaks down, and so you have to try to do something else. Another thing that I would like to mention is a kind of discrete variant of this problem, which was studied by Garber and Sepulveda also very recently, where they try to do the same thing, but for the discrete Gaussian free field. So they are given the values of the discrete Gaussian free field modulo some parameter, and then what they actually show is that if this modulo is not too small, then you can actually recover the field, and there is a transition where the recoverability becomes impossible. And in fact, the result we have with Johan is it gives also a lower bound for this transition, this threshold temperature in the discrete case. Because they show that if you can recover in continuum, then you can also recover in discrete. Okay, so let me just give some heuristics to think to see how one would approach this problem. So if g is a continuous function, and I look at some function f, which is just given by the exponential of I beta times g, and I would like to recover g just by looking at f. And surely this is then possible because I can just locally look how does the angle change. If the angle grows, I know that the function has to grow, and if it goes smaller, I know that the function has to decrease. And in fact, the same holds even if g is not continuous, but if you a priori know that it doesn't have too large jumps, then you can still do this kind of tracking. And so you would hope that actually the distribution x would in some sense be not too rough, that you could still do some kind of tracking. And kind of a nice way to restate this heuristic is maybe to consider the case if g was even differentiable, then you can actually write the formula for the gradient of g. It's just the gradient of f divided by this I beta f. So you have a nice formula, and then you can start playing around with this, and maybe this will give you the proof. And that's eventually what happens, but there are a lot of details that you have to take care of. So here's the theorem. So first of all, it only works if the dimension is at least 2. And in this case, for any beta in this subcritical phase, you can locally recover the distributional gradient of the field from the imaginary chaos. And then, of course, if you know that the x itself has some boundary conditions, then you can often just fix the global constant, and you can really recover the field itself. So let me just give a short, brief slide on the idea for the proof for d larger than or equal to 3. So what you start with is pretty carefully chosen observables. So you look at these random variables h eta, where I see you are going to say something.
Within 1 minute or so, would that be okay?
Sure. So here you have this, you just put in these imaginary chaos objects, and you have this kind of normalizing factor here, and then you take the partial derivative of phi eta, which is a smooth approximation of this delta of the Dirac delta function. And okay, so this is to recover the first partial derivative, and you can just put another coordinate here to get the whole gradient. And then you show that actually these guys converge to minus I beta times the distributional derivative of gamma applied to f. And you can see this formally by integration by parts, because if you do that, if you move the derivative along the u to this other term, you will get this thing here in the parentheses, but you still have this thing that converges to Dirac delta. And what it does then is that basically these two things cancel, and here in the exponential everything cancels. This is very formal, of course, and you get the right limit. But of course here, for example, the CUU is it's infinite, so it doesn't really make sense as such, and you have to be very careful. So there are a lot of singularities everywhere, and what you show is that converge in L2. If D is 2, then you have to do something more clever, but you can still do it. You look at kind of an average of this H eta case, with the eta case going to 0 very fast, and you get rid of a certain resonance phenomenon that would otherwise kind of ruin your day. And finally, if D is 1, then I'm not sure if it's going to work or not, so it's still open. So I think that's it, and thank you.
All right, thank you very much. Do we have time for one quick question, if there is one? So online I did not follow, not so fun. Okay, so if not, well, thanks again. And we can move on to today's final speaker, who is going to be live. Okay, so the final speaker for this afternoon is Johannes Alt from the University of Geneva and from New York University, who's going to talk about the Poisson-statistics for extremal eigenvalues of subcritical Erdős-Rényi graphs.
Okay, thank you. Thank you for the introduction and also for the opportunity to present some of my research here. What I'll talk today about is the Erdős-Rényi graphs and their Poisson-statistics at the spectral edge. And this is joint work with Raphaël Ducarté and Antti Knowles, who are both here. What I'll start with is some introduction to random matrices. So originally they were first introduced by Wishart in the 1920s and Wigner in the 1950s. So actually they both had, both of the motivations to define them came from applications, and since then random matrices have found many more applications. For example, in nuclear physics, solid state physics, or wireless communications, and also neural and biological networks. Moreover, they have found many applications or connections to other areas in mathematics, for example, operator algebras, number theory, or also random growth models. And the goal of today's talk, and also in all of these applications, is to study and understand the eigenvalues and eigenvectors, because they are the fundamental objects of interest, both from a mathematical point of view, but also in the applications. Since basically Wigner in the 1950s, one core theme of random matrix theory has been the universality phenomenon, which states that microscopic statistics are independent of the actual details of the model. So what do I mean with this? So first of all, microscopic statistics are statistics that live on the typical space of the eigenvalue fluctuations, and independent of the model means that it only depends on a few basic properties of the model, and is independent of the precise description of the model. And yes, I already mentioned it goes back to the Wigner, which introduced it in the 1950s. And since then it has been refined to somewhat more precise group of questions. Namely, one wants to distinguish which random matrix models belong to the random matrix universality class and which belong to the complement, which I abbreviate with RMUC or RMUC complement. The characteristic features of the of models that are in the random matrix universality class are that one sees random matrix eigenvalue statistics for the eigenvalue fluctuations on the microscopic level, and also the eigenvectors. They show a delocalized behavior, which means that the mass of the eigenvectors is basically uniformly distributed among its components. And one important feature is also that in this case the eigenvalues will be strongly dependent on each other, and actually they will repel. In the complementary regime, or in the complementary class, the eigenvalues show Poisson eigenvalue statistics, and in particular the eigenvalues become independent of each other, and the eigenvectors are localized, so that means that the mass of the vector is concentrated on a few vertices, or on a few components of the vector. And now the objective for the rest of the talk, or in this area now, is that to prove which models belong to this random matrix universality class and which models belong to the complement. And actually, as already the title suggests, today I focus mostly on the complement. And the model I want to study is the Erdős-Rényi graph, which is a very simple model for undirected random graphs. So we start from n vertices, here labeled by 1 up to n, and then a pair of vertices is connected with probability d over n, where d is an independent parameter, and all of these edges are drawn independently of each other. So as you see, it's probably the simplest model of a random graph you could come up with, but nevertheless it shows very intricate behaviors. For example, it has some connectivity transitions depending on depending on how the d parameter is tuned. And what I'm interested in is actually to look at the adjacency matrix of such an Erdős-Rényi graph, where d is still an independent parameter, and we will send the n to infinity. To just give you some impression of what happens here, I want to start with some classical result, which goes back to Wigner. One looks here at the eigenvalue density, so you can think of it as drawing a histogram of the eigenvalues to see where most of the eigenvalues accumulate. Actually, they more or less all between -2 and 2, and in the limit when n goes to infinity, as long as d goes to infinity, you see this semicircle distribution, which also appears in many other random matrix models. And to give you now an overview over what kind of results have been proven, specifically to the question which models are in the random matrix universality class, or for what parameters of d we are in the complement. I give you here some kind of phase diagram. I first start about the question of eigenvectors, so where the eigenvectors are delocalized and localized. So what you see here on the x-axis, we see the spectral parameter, so that's the -2, 2, which you've seen in the, or it corresponds to the scale of -2, 2 in the previous plot. And on the y-axis, we see the dependence on the parameter d. So here for the gray results, basically proved, one part of what they proved is that there's actually no spectrum between outside of -2, 2, as long as the d is sufficiently large. And then in these, and then the red works here basically proved that above here, when the d is bigger than a constant times log n, then you have delocalized eigenvectors everywhere. And what we recently proved with Raphael and Antti is that down here, when the d is smaller than log n divided by log 4 minus 1, you actually get a new phase, so the eigenvalues leave -2, 2. That had actually already been known previously. But then you have this dichotomy between certain eigenvalues are delocalized, namely the ones between -2 and 2, and outside you have localized eigenvectors. And actually, you can learn more about this transition for the eigenvectors in Raphael's talk. He will talk next week on Tuesday at 6:30 in the session of the ICMP on probability and random structures, I guess that's how it's called. And today what I want to talk about, as I already said, is I want to talk about the eigenvalue statistics. And what has been known basically already for a few years is that when the d is bigger than n to the epsilon, you have random matrix eigenvalue statistics all the way between -2 and 2, so for all eigenvalues. And the result I want to present today, which is our new result, is that here at the spectral edge, when the d is sufficiently small, you actually have Poisson eigenvalue statistics. Yeah, to be now a bit more precise, so yeah, I want to define by sigma d this curve here actually, which describes the edge of the spectrum as a function of d. One can actually get a deterministic expression for this, so that's then the expectation of the largest eigenvalue, so to say. And our theorem reads as follows. So as long as the d is somewhat bigger than log n to the 4, which we think is due to some technical constraints, and then as long as the d is smaller than this threshold where the eigenvalues start to leave minus 2, the eigenvalue is close to the edge, close to the spectral edge, to the sigma d here. They form a Poisson point process, and we also can determine the intensity measure explicitly. As a corollary of this result, one also gets the distribution of the largest eigenvalue, or of the second or third largest eigenvalue, and so on, or of their joint, or of their joint distributions that basically just working with the Poisson point process then. And as another interesting result, we also get that the eigenvector corresponding to these eigenvalues is exponentially localized. So if in the following sense, so if W is an eigenvector corresponding to an eigenvalue which is sufficiently close to the spectral edge sigma d, then it's exponentially localized, where by that we mean that there's a Q which defines the exponential decay that's smaller than 1, and the vertex x, such that if I restrict the eigenvector to the complement of a large ball in the graph distance around x, then this mass will basically behave like q to the I divided by this other factor here, plus some tiny error term. And yes, I already explained in words, so the BI is the ball in the Erdős-Rényi graph distance. Okay, so these are the results, and then in the remaining time I will focus on giving you some proof ideas. So the first observation, which was already made in some of our previous works, is that for every eigenvalue lambda of this rescaled adjacency matrix, whenever we have an eigenvalue that's bigger than 2, we actually find the vertex whose normalized degree. So I gave the definitions down here. So the alpha x is the number of neighbors of x normalized by d, such that this is bigger than 2. Then we find that the eigenvalue is actually close to this explicit function lambda of alpha x up to some small error term. And the idea now is to improve this error. One is what one calls a rigidity estimate. We have to actually improve this, or the basic idea is to improve this such that the error term becomes of this order, because there are some heuristic arguments using perturbation theory. One can see that actually one expects the fluctuation of this eigenvalue lambda to be of order 1 over d. So that means that if we assume that we can somehow have a similar estimate here and reduce the whole problem to a simpler random variable, then we better prove a rigidity estimate which is of this order. And then once we would have proven such a statement, we could identify the fluctuation by understanding the fluctuation of some other random variable of this type. How much time do you have left? 5 minutes. Okay. So as I now indicated, we need to prove some very precise rigidity estimate. And as the previous slide already indicated, somehow those vertices are interesting to us where the alpha x is sufficiently large. In fact, since this function lambda is monotonous, we basically want to study the vertices whose this normalized degree alpha x is actually close to the maximum. And in this setup, one can study the vicinity, so a large ball in this Erdős-Rényi graph. One can study it very precisely, and actually what one will see is that if I restrict the graph to such a ball, then actually we will obtain a regular, or something which is close to a regular tree. And so then to a certain extent it reduces to understand this approximate regular tree. And the important insight here is, because we now have to basically determine the largest eigenvalue there very precisely, it's an important insight to find a basis, or a suitable basis, where the restricted matrix becomes tridiagonal, But nevertheless, the trigonal matrix should still be in such a way, should still be so simple that we can still understand it in a, in an explicit way. And actually, it turns out that one can choose a basis such that this matrix becomes approximate tridiagonal and very close to something that has this structure. And yeah, so now the important random variables here are the alpha x and the beta x. The alpha x you already know; these are the number of neighbors of the neighbors of x appropriately normalized. And now the b of x is so to say the next order. So we look at the neighbors of x and their number, and then it turns out that the right normalization for this beta x is d squared times alpha x. And from this analysis, which I now summarized on this slide, we obtain that the largest eigenvalue of h restricted to this ball BR of x is close to the largest eigenvalue of this tridiagonal matrix, which I denote by lambda d of alpha x. And then actually one can also prove that the eigenvector of this restricted matrix decays when the R is sufficiently large. So one can then translate this result about the eigenvalue of the restricted matrix to the full matrix, and then one can obtain this final rigidity statement, which I said is the main step here. Now we would be almost done to get the Poisson statistics if these random variables were all independent in X, but they're not. But on the other hand, the correlations are actually rather small, so one can work out one can study them in detail and obtain that the joint distributions actually factorize when the n goes to infinity, and in that way we also we can also determine the intensity measure of this Poisson point process, which is a combination of the asymptotic distributions of the alpha x and beta x. Okay, that's all I wanted to say, so I'll just briefly summarize. So at the spectral edge, we proved that if the d is smaller than log n divided by log 4 minus 1, and there's also some technical lower bound on d, then we obtained Poisson statistics for the eigenvalues and the localization of the corresponding eigenvectors. And so hopefully I convinced you that these Erdős-Rényi graphs are an interesting example of a random matrix model. And here, just to have an outlook, this is the expected phase diagram, so there's still some work to do here. And thank you very much for your attention.
Thank you very much. Are there any questions? Online? Okay, seems not. Then thank you again. So this was it for today. So once again.